Question 3. Lightning occurs when charge builds up in the creating potential difference between the ground and the atmosphere. During the lightning strike, there is an average current of 3.3 times 10 power 4 ampere for a time 2.6 times 10 power negative 5 second. Calculate the charge transferred during the lightning strike. We write the equation of current I equals Q over T. Q equals I times T. Current, as you see here, 3.3 times 10 power 4, and the time is 2.6 times 10 power negative 5, which is equal 0.858 coulomb. 0.85 or 6. The potential difference between the ground and the atmosphere is 3 times 10 power 7. Calculate the average power in gigawatt transferred during the lightning strike. Power equals I times V. The current is 3.3 times 10 power 4, and for the potential difference 3 times 10 power 7 times 10 power 11 watt. 990 times 10 power 9 watt, which means 990 gigawatt. 990 gigawatt. A lightning rod is attached to a tall building to conduct a charge safely to the ground. The lightning rod is moduled as a uniform cylindrical copper cable of total length 95 meters that runs from the ground to the top as shown. Here we have the lightning rod, this wire here, from the top of the building to the ground. The resistance of the lightning rod is 9.6 ohm. The resistivity of copper is 1.7 times 10 power negative 8 ohm. Determine the radius of the lightning resistance equals rho L over pi R. R equals rho L over pi R, which is equals 7 times 10 power negative 8 pi, and pi, the resistance is 9.6, equals 2.315 times 10 power negative 4 meter, which it equals almost 2.3 times 10. The radius of copper lightning rod is doubled with no change to its length. State the effect of the charge on the resistance of the light. From the equation, R is proportional to 1 over R squared. So it means when the radius increases to double, the resistance decreases by factor of 4. Resistance decreases to quarter. Okay, because we have a square, so resistance decreases to quarter. A section of the lightning rod of length 0.12 is removed for testing. A tensile stress of 1.9 times 10 power 6 Pascal is applied, as shown in figure 3.2. The section of the rod obeys Hooke's law. The Young modulus of copper is 1.3 times 10 power 11 Pascal. Calculate the extension of the section. Young modulus E equals Young modulus equals stress over strain. Stress, we have the value of stress, but strain equals x over L, extension over original length. So it equals sigma stress times length divided by x. So just the equation to find x. X equals sigma L 1.9 times 10 power 6. The length is 0.12 divided by Young modulus 1.3 times 10 power 11 equals 1.754 times 10 power negative 6 meter. 1.8 times 10 power negative 6 meter. Question 4. A pinball machine uses a spring to launch a small metal ball of mass 4.5 times 10 power negative 2 kilogram up a ramp. The spring is compressed by 8 times 10 power negative 2 meter and held in equilibrium as shown in the figure. The ramp is an angle of 15 to the horizontal. The spring obeys Hooke's law and has a spring constant of 29 Newton per meter. Calculate the elastic potential energy in the compressed spring. E equals half kx square. We have half x here, the spring constant 29. X is the extension as we have here from the graph, 8 times 10 power negative 2 square equals 0.0928 joule. 9.3 times 10 power negative 2. The spring is released and expand quickly back to its original length. Calculate the increase in the gravitational potential energy of the pole when the spring returns. The increase in the gravitational potential energy equal mgh. H here is the vertical height. We can figure the vertical height from the triangle. If we draw this triangle, the hypotenuse of the triangle is the extension here, and the angle here is 15. So we can say the vertical height here equals the hypotenuse sine theta, 8 times 10 power negative 2 sine 15. Potential energy equals mgh. Gravitational potential energy equals the mass of the pole, 4.5 times 10 power negative 2, g 9.81, and for the height 8 times 10 power negative 2 sine 15, 9.14 times 10 power negative 3 joule. We can approximate it to 9.1 times 10 power negative 3 joules. The pole leaves the spring when the spring reaches its original length. Assume that all elastic potential energy of the spring is transferred to the pole. Calculate the speed of the pole as it travels the spring. When the spring is released, the elastic potential energy changes into gravitational potential energy to raise the pole up, and more kinetic energy. So we can say that elastic potential energy E equals the gravitational potential energy, and the kinetic energy equals E, elastic potential energy minus gravitational potential energy. Elastic potential energy we calculated here 9.3 times 10 power negative 2, and for the gravitational potential energy 9.1 times 10 power negative 3, which equals 0.0839 joules. So the kinetic energy equals, which equals half mv square, equals 0.0839 joules. So we will derive this equation to find v, speed or velocity. V equals the root of 2e kinetic energy divided by m, equals the root of 2 times 0.0839 divided by the mass, 4.5 times 10 power negative 2, which equals about 1.93 meter per second. Final answer 1. The ball comes to rest on a horizontal trapdoor. at distance d from its pivot. A force F acts vertically downward at distance 2 centimeters from the pivot, as shown in figure. The trapdoor is in equilibrium when the force equals 1.7. Calculate d. Here we'll apply the rule of moment. It is in equilibrium, so the clockwise moment equals anti-clockwise moment. F1 d1 equals F2 d2. For F1 here 1.7 and the distance is 2 centimeters. We convert it to meters, so times 0.02 meters equals, we have the mass 4.5 times 10 power negative 2 times gravity 9.81 times the distance equals 0.077 7.7 times 10 power negative 2. Force F is decreased 1.7. Force here decreased. State the direction of resultant moment about the pivot. When the force decreases, this side moves up and this side will rotate in this direction, means clockwise.